Hello all, I'm Cyril Naves, and I would like to present our work, A Choice of Ethereum Clients for Private Blockchain, an assessment from proof of authority perspective. This work was done as part of my doctoral work along with Renault Software Labs Severine Glock and Patricia Guitton, and from University of Côte d'Azur, Professor François Verdier. The motivation of our work is that there exists a huge ecosystem of clients in the Ethereum space, and we would like to test them and measure the performance of each of the clients. And we'd like to test it from a private perspective, basically a private network space, mostly in the enterprise context, since the enterprise context would demand a kind of a privacy and security of the data networks. So we would be mostly concentrating towards the proof of authority perspective, since it's more efficient compared to the proof of work consensus algorithms. I will be concentrating more on Parity, Geth, and Besu, since they're the most prominent of the clients which are available in the ecosystem space. Comparing the three prominent clients, Geth, Parity, and Besu, Geth is written in Go and Parity in Rust, and Besu in Java, respectively. The implementation of power consensus algorithms are named as Click Aura and Click EBFT 2.0 by Besu. That the persistence layer maintained by Geth is level dB, while that of Parity and Besu is ROX dB. The contribution of work is the construction of a use case agnostic performance testing tool for measuring the performance of each of the clients. And second one is a study of the performance of the clients from an Ethereum-oriented perspective parameters. And third one is the uncovering of issues and limitations in each of the clients, which are reported responsibly to the community. And the last one is the construction of a load balance architecture, which is very specific to Ethereum context, since it varies with the normal load balance architecture. Next, we talk about the test topology of an Ethereum private network. Ethereum private network is based out of Microsoft Azure VMs, and it's Western Europe VM with each of RTT average of 1000 microseconds. And then each VM is an Ubuntu 18 VM with 2 vCPU and 8 GB RAM. The blockchain network is simple. To be simplistic, it comprises of 3 nodes, and it's discovered by a boot node. And each of the nodes is equipped with a tool instance deployed on it, and which interfaces with a log DB, with basically the NoSQL DB to store all the transaction stats for measuring the performance. The idea behind this test topology is to measure the throughput. The throughput is derived by the transactions per block divided by the block period in a proof of authority context, because the proof of authority context mines blocks for each of the block period time. And then the transactions per block containing is measured by the block gas limit and divided by the transaction gas, the gas which is measured in terms of the Ethereum context. And then the version of clients deployed inside the test is basically Geth, which is 9.18, and OpenEthereum 3.01, and Besu 1.50, almost the latest clients which are available at the point of test. 3 nodes and the 3 clients which are deployed for testing. Next is the architecture of the tool. The properties of the tool which makes it different from the existing tools used for measuring the Ethereum network's performance are basically the ASIC producer consumer emitter pattern. Basically stocks up the queue inside a queue, and then we spawn up a number of threads which acts on the queue and which sends the transactions in a faster pattern to the network. The next one is a predetermined ordered nonce management, which effectively speeds up the process of ordering the transactions and effectively also avoids the problem of non-ordered transactions, and then avoids the problem of invalid transactions as well. And next, we have the raw choice of message protocol, which basically avoids the latency caused by various message libraries which are used for interfacing with the network. This is the overall architecture. The overall architecture comprises of a transaction emitter, which sends all the transactions to the queue, and then which queue is then operated by various threads which are acting on the queue, and then sends the transaction to the network. The transactions are nonce managed, and then the RPC WebSocket payload is used to send the transactions. Next, what is the type of transactions tested inside the network? The type of transactions are basically smart contract functions, not the usual crypto money transactions, because we want to test the real-time use cases used inside the enterprise world. And basically, the choice is smart contract function, basically to increment 3 variables. The idea is to abstract the increment operation, mostly used in token standards, or it can be mileage increments in case of vehicular use cases. And second one is simple maps smart contract function. So BAP is a commonly used storage structure, which is most commonly used in smart contract use cases. So we wanted to test out by incrementing 3 variables and storing them inside the map structure. Next is the evaluation of the proposed tool against the existing tools, basically Chainhammer and Caliper. Chainhammer is brought about by independent developer, and Caliper comes out of the Hyperledger framework. We find that the proposed proposed tool basically in 2 versions, HTTP and WebSocket protocol format. It performs much better than the existing tools. Also, we notice that the Geth performs much better. It scales well compared to Parity, Besu, etc. And then we also increase the number of threads in our client, basically the WebSocket client. And then we notice at the level of 10,000, we notice a huge amount of 2,000 transactions per second, which is quite promising. But in the earlier version of Geth, it's 9.12, we noticed a stalling issue due to the inefficient caching, inefficient LRU cache, so which is eventually improved. And then in 1.9.8, which was eventually fixed. So it was basically stalling of the network, which was fixed. We reported it to the community, and it was subsequently fixed. So we noticed that the Geth here scales very well, and Parity has an inbuilt bottleneck issues, as well as Besu inbuilt bottleneck issues, which we'll uncover in the forthcoming slides. Next, having chosen the number of threads is 100, we perform the Ethereum specific alliances by varying the block gas ratio from 1000, 3000, 6000, and up to 15,000. The increase of the block gas ratio, basically it accommodates more transactions inside each blocks, which also puts more load on the network. We notice that at block gas ratio of 6,000, we notice a peak, and then eventually it drops. Why does it drop? Because that greater than 6,000 block gas limit, we notice that eventually there is a stalling inside the network. Basically, it slows down the transaction. It was due to EIP 155 signer, which was pointed out by the which was pointed out due to the logs, and this was pointed to the EIP 155 signer of recovering a public key from a signature. So this is an existing bottleneck. So if we go beyond 6,000, it eventually hampers the network. Next, Ethereum specific alliance with respect to the block period variance, since we have a proof of authority which churns out block with every block period. So the minimum is 1 second, 2 seconds, 3 seconds, up to 15 seconds. We tested for each of the clients, and we noticed that at a block period of 1 now, we noticed that there was a lot of inconsistencies inside the network. There were a huge number of forks inside Geth network. The others, basically the Parity and Besu, their performance is already throttled. While Geth, it has some variance with respect to each of the block period times. So block period 2 was eventually the best here, as is pointed out. The one was very fast, and the others eventually it's more slower churning out of blocks 3 and 8 and 15. Basically, the TPS reduces here. We also reported this issue to the Ethereum community, which is being followed. Next is the construction of the Ethereum specific load balance architecture. It comprises of a transaction emitter, similar to the tool which is earlier discussed. It sends a transaction to an Nginx load balancer, which operates on a round robin based algorithm, and then it redirects the request towards each of the middlewares. The middlewares are interfaced with each of the respective nodes, blockchain nodes. What is contained inside the middleware is basically the RabbitMQ transaction queue, which serves all the incoming transactions. And this transaction queue is worked upon by the transaction processor, which is an independent worker process, which acts on the queue in the first in first out basis. And then it takes out each transaction, and then it constructs the transaction by deriving the nonce cache based out of Redis, because this is necessary in order to maintain a ordered nonce management. And then it's finally broadcast the transactions to each individual node. So what is the analysis of non-load balance with non-balanced transactions per second for each of the clients as well? So if we notice that non-load balanced, it has much greater performance compared to a load balanced architecture, because in load balanced architecture, we have certain inbuilt bottlenecks, basically the storing of the transaction inside the queue, and then working of the transactions by each of the worker process, and then getting the nonce cache, and then constructing the payload, etc. But the advantage within the load balance architecture is basically the reliable broadcast of the transactions in case of the node failure in the blockchain, and then the transactions are already stored inside the queue, which can be later processed upon eventual recovery. So what are the client issues which we discussed? The first 3 issues are already discussed. And the fourth issue is basically the fork deadlock, which we noticed inside the click POA algorithm, proof of authority algorithm. So which was also mentioned to the community back. So it's basically fork deadlock is unresolved. Normally the forks had to be resolved. So it needs to be modified difficulty calculation. And next, the others are basically the bottlenecks, which I already discussed in other clients, basically at Parity and Besu. There was transaction API failures, HTTP timeouts, because the client installs large transactions which are stored inside the queue. And the lesser throughput in Git, basically it was due to the high input output on the RocksDB operations, persistent operations, and also as well as the ACCP256K1 hash library. The hashing function needs to be improved. There's already inbuilt problem inside the hash library. And in case of Besu, there was a lot of timeouts, basically a similar case of Parity. And the issue was pointed out to the bouncy castle library of the Kekaka digest. So it was slowing down the calculations of the hash. This basically pointed out. So as per the reported issues, Geth performs better than the other clients. And the positives are the performance testing tool for Ethereum network was devised, which is better than the other tools. The clients were analyzed, and each of the issues were reported to the community, and the new load balance architecture was proposed. The drawbacks are basically the security aspects of the clients were not discovered, and they were not analyzed as well. The load balancing has to be improved, basically to include the transaction type balancing, basically look at each of the transactions, then reroute the transactions, and basically the middleware can also be improved. Yep. So thank you very much for listening.